Okay, we're going to look in this discussion at phase changes involving solids. Okay, melting point, temperature at which melting occurs, and when we're talking about the energy required to melt a substance, we are talking about the enthalpy of fusion. So that's the quantity of heat required to melt a given amount of a solid. Okay, sublimation, that's going to be a transfer or a transition from a solid to a vapor. And then it gives you kind of an example of a common form of sublimation. And again, when we're talking about how much energy does it take to cause that transition to occur, we're talking about the enthalpy of sublimation. And then triple point, when we are talking about phase diagrams, your triple point is going to be the place where you have all three phases in equilibrium, which is also where the line on the phase diagram that represents your solid-liquid transition and your solid-gas transition, it's the point where they meet. Okay, so here are some enthalpies of fusion, just to kind of give you an idea of those, and these are provided along with the corresponding melting point for the substance. And remember, this melting point is the normal melting point, which means that it occurs at 1 atmosphere of pressure. Okay, heating curve. For this one is for water, and the way that you can tell is that, let's get our pen going. All right, is that right here? Here we're going from solid here to this flat line here. That's our melting occurring right there, and so the temperature at which that phase change happens is our melting point. And so on these heating curves, we have, here we are heating the solid, so the energy put in, and this has time here, but basically this should say we are adding energy at a constant rate. And so that's why sometimes these heating curves will use time on the x-axis rather than energy added. But they are equivalent as long as the energy is being added at a constant rate. So we're adding energy, and so as we add energy as the solid, our temperature is going to increase until it hits the melting point, at which time then the heat that's being added, instead of being sensible heat is what we see where the heat added is causes a change in temperature here. Okay, when we are adding heat, we have no change in temperature. We're causing a phase change. That's called latent heat, or sometimes referred to as hidden heat. Okay, so this is kind of the heat that's being stored here while this phase change is occurring. It's not being, it doesn't result in a temperature change. Okay, and then again, once we have transition, so this would be the point right here. We're all solid, and then we get a mixture, solid, liquid, and then at this point, we have melted all of our solid, and then now the heat added goes into increasing the temperature of the liquid. Okay, here is a cooling curve for water, and the main thing that they want you to notice here is that sometimes if you're doing cooling water in a lab, and especially if you're cooling it fairly quickly, you will see the temperature drop down below the melting point. It's a phenomenon referred to as supercooling. but it will drop down, and then as the molecules orient themselves and we start to crystallize, then we start to see our nice flat phase change. And so we would be liquid, and then at this point all of the liquid is now frozen into the solid, and then the solid starts to decrease in temperature. Okay, so now let's look at some calculations involving these heating curves. And so there are a couple of types of problems that I would expect for you to be able to work. One is pretty much just a straight, how much energy does it take to do this? So here we have 5 grams of ice at -4 degrees Celsius, and we want to heat it to liquid water at 25 degrees Celsius. The first thing to do is let's just draw this heating curve, okay? All right, and we only need this piece of it because we're only going to liquid water. So we know we're going to start right here at -4 degrees, okay? And we know this is water, so that's 0 degrees at the melting point. And then we're going to stop in here at about 25 degrees Celsius. Okay? All right, so what do we need to know? Well, the thing to know is that we're going to calculate the amount of energy that it takes to transition each piece of this curve. We're going to calculate that separately. Okay? If we are in a single phase, like a solid, all liquid, all gas, a single phase, in order to calculate the amount of energy required to change the temperature, we use, from previous study, specific heat. Okay? And for water, for a liquid, and we pretty much only dealt with the specific heat of liquid, but you should realize that all 3 phases of water has its own specific heat value. And so if we're talking about, we need it for a solid, so C of the solid, water, and C of the liquid. And which is the same thing. I think our book uses S. I'm sorry. When I learned it, it was C, or C sub P, not S. But so bear with me. So anyway, I'm looking for some of these. There are constants here. We know for liquid it's 4.18 joules per gram degrees Celsius. And for solid, here we go. Okay, it is 2.03 joules per gram degrees Celsius. And I'm not sure where else in your book it has this, but if you need this information for each of the pieces of this curve, if you go to page 480, problem number 87 has all of the information that you need for the entire heating curve of water. Then we're going to melt, so we need a delta H of fusion, which this one gives me that it is 6.02 kilojoules per mole. Okay? Alright, so now let's look and see what we've got here. We have, let's see, we're going to need moles there and grams for that one. So let's go ahead, and we have 5 grams of our ice is going to equal 0.277 moles. Okay, so now I think we've got all the information that we need. And so our total energy is going to equal the energy to heat the ice plus, oh wait, let's go back here. I don't want to use E for this. Because what letter did we use for heat before? we used Q. So Q total is equal to Q to heat our ice plus the Q to melt plus the energy to heat the water. Okay, and so we have MC delta T or MS delta T for specific heat. So to heat the ice, it's the mass. I have 5 grams times the specific heat of the ice, 2.03 joules per gram degrees Celsius. And my delta T, I'm going from -4 to 0, so that's a 4-degree transition. Okay, that's going to be in joules, so I'm going to just leave it in joules, and I'll convert my melting into from kilojoules into joules. So then to melt, it is the number of moles, 0.277 moles. I'm going to have to go kind of down here. Let me block off my little constants here. Sorry about that. Times the enthalpy of fusion, 6.02 kilojoules per mole. And remember, we're going to add these together, so our units have to match. So I'm going to take and say 1 kilojoule, 1,000 joules, so that's going to be in joules. And then again, I have 5 grams times 4.18 joules per grams degrees Celsius. And now I'm going from 0 up to 25, so I have a delta T of 25 degrees Celsius. And so I'm just going to add all of those together. So So if I haven't made any mistakes in that, I get 2,230.6 joules. Okay, another type of problem that you'll have is one where they tell you how much energy you have, and then they want to know, is this enough energy to melt this much, or what state will this be in if we add this much energy to it, and what will its temperature be? That sort of a question where we have an amount of energy. And so what we're going to do is, again, start out, let's draw our curve. Okay, so we have ice here. All right, here's our, like that. But here, we're starting out ice at 0 degrees. And we don't know where we're going to end up, all right? So we're just going to kind of look at it one step at a time. So I know I have 60 grams of water, and that is, we're going to just get some of this out of the way, these little calcs. All right, so that's 3.32 moles of water. And then what am I going to need? Well, first, don't need my specific heat, but I need that delta H of fusion that I used in the previous one, and that was 6.02 kilojoules per mole. All right, and so here we have, let's just look at the first step. So the first thing it's going to do is it's going to melt. So the energy to melt is going to be the number of moles. And again, if you're not sure of these equations, look at the units. All right, it's energy. We want to end up with either joules or kilojoules. Okay, and so in this case, with this enthalpy of fusion, I just need to multiply by the number of moles, so my moles cancel out, and I get kilojoules. So that will give me 20.0 kilojoules. All right. So then what I'm going to do now is I'm going to subtract. So what I start with minus what I used to melt. So I have 130 kilojoules left. All right. So now, what's the next thing? So now that puts me right here. So now what I'm going to do is let's see if I have enough to take it from 0 to 100. All right. Let's see if I have enough energy to even get it up to the boiling point. So Q to heat the water is going to be my mass times specific heat of the water. And then my delta T is 100. I'm going from 0 to 100 degrees. So that is 60 times 25080 joules, which is 25.08 kilojoules. So again, I had 130 kilojoules minus the 25.08 kilojoules to heat the water to 100 degrees, and that leaves me with 104.92 kilojoules. Okay, so now I want to see if I have enough to make the transition to boil the 60 grams of water. So now I'm going to need my delta H of vaporization, and again, looking that up, it's 40.7 kilojoules per mole. So Q to boil is going to be 3.32 moles times 40.7 kilojoules per mole. That's going to equal 135.1 kilojoules. That's what I would need to boil the 60 grams of water, and I only had about 105 kilojoules at the time that I reached the boiling point. So the answer is no, I do not have enough energy to boil the water. I would be able to boil some of it, but not all 60 grams. So there you have it. That's kind of the two basic approaches to doing calculations with heating and cooling curves.